Hello students, this is Yogita Tatar, subject teacher of Engineering Mathematics from Sri Siddheshwar Women's College of Engineering, Solapur. As we know that we are dealing with the first unit of M3 syllabus, that is Laplace transform, and we have studied 4 to 5 properties and solved some of the examples based on those properties. Now we will move to the next property, that is the next result, Laplace transform of derivatives. We have seen how to find the Laplace transform of integral. Now we will move to the next part, Laplace transform of derivatives. If f of t is a function and we are asked to find Laplace transform of its derivative, that is f dash of t, then the formula is L of f dash of t equal to minus f of 0 plus s into Laplace transform of the original function f of t. So you are given one Laplace transform, you are given one function of t. First you have to find its value at t equal to 0, and this value is nothing but here minus f of 0. And then for the second term of this result, you should find the Laplace transform of the original function and multiply it by s. So in this way you will get the result for Laplace transform of first order derivative, that is f dash of t. Now second order derivative, L of f double dash of t, then minus f dash of 0 minus s into f of 0 plus s square into Laplace transform of the given function f of t. Just observe these two results. Here first order derivative, so in RHS there is no any derivative, and the last term is positive. Here second order derivative and the last term is positive and it is multiplied by s square. Here it is multiplied by s, here it is multiplied by s square. Here Laplace transform of first order derivative, so multiplier s is having degree 1. Here Laplace transform of second order derivative, so multiplier is having degree 2, that is s square. And first order derivative 1 plus 1, 2 terms are there in the formulae. Here second order derivative 3 terms are there in the formulae. So in this way we have to use the Laplace transform of second order derivative of the function result. Okay, the third one, Laplace transform of third order derivative. Obviously third order, so 3 plus 1, 4 terms should be there. Okay, there are 4 terms, only the last term is positive. The third order derivative, so here s cube, index of s is 3 and index of s is decreasing here. So s cube, s square, s and s raised to 0, that is 1. Here s square minus s, that is s square, s and s raised to 0, 1. Here s and s raised to 0, 1. So minus f double dash of 0 minus s f dash of 0 minus s square f double dash of 0 plus s cube into Laplace transform of f of t. So here in these results only the last term where we multiply the Laplace transform of the original function by the corresponding power of s, that term is only positive, otherwise the remaining terms are with negative sign. And in this way we can find the Laplace transform of any order derivative of the given function of t. But these three results are frequently used, and this result is very important for the most important application of Laplace transform, that is to solve the differential equations. Okay, now we will solve 2 examples using these results. Given f of t equal to sin t by t, find Laplace transform of f dash of t. So obviously first you should have the Laplace transform of this f of t. As we have seen, we have solved so many examples till now. So first you should find the Laplace transform of sin t and then apply the division by t property, so that you will get the Laplace transform of sin t by t. Okay, we will see the solution. Here f of t equal to sin t by t. So the Laplace transform of the original function f of t, that is sin t by t, I have written here directly. As we know, sin t Laplace transform result is 1 upon s square plus 1, and for division by t property we have to take its integration from s to infinity with respect to s. What is its integration now? So it is tan inverse of s. We know the result 1 upon 1 plus x square, its integration with respect to x is tan inverse x. So here instead of x they have used s. So it is tan inverse s, but this is definite integration within the limit s to infinity. So upper limit substitution, tan inverse infinity minus tan inverse of s. Tan inverse infinity pi by 2. So pi by 2 minus tan inverse s, cot inverse s. So this is the Laplace transform of f of t, that is the original function which we are going to use to find the Laplace transform of f dash of t. But before that we should have f of 0 value. So as f of t is sin t by t, so it is f of 0 is sin 0 by 0. But as we know, sin 0 value is 0. So denominator is also 0, numerator is also 0. This is not at all 0. This is indeterminate form, and here we have to use the L'Hospital rule or limit as theta tends to 0 theorem result. So here we are using this result to find f of 0. Instead of sin 0 by 0 we have to write limit as t tends to 0 sin t by t, and this is the very famous result from the concept of limit and continuity of the function, and its value is 1. This is very important result. Some students write it directly 0 and hence their answer is wrong and they lose the marks. But remember, limit as t tends to 0 sin t by t is always equal to 1. Now we have to use Laplace transform of derivative result. So L of f dash of t equal to minus f of 0 plus s into Laplace transform of f of t. So here f of 0 value is 1, just now we have obtained. So it is minus 1 plus s as it is multiplier, and Laplace transform of f of t is cot inverse of s. So it is minus 1 plus s cot inverse s, or you may write this as s cot inverse s minus 1. You may write positive term first and then the negative term. Okay. In the same way we have to find the Laplace transform of derivative of the given function. Now we will solve one more example. Using the same method we have solved here one example. These examples are really unique one. If Laplace transform of 2 into square root of t upon pi equal to 1 upon s raised to 3 by 2, show that Laplace transform of 1 upon square root of pi t equal to 1 upon root s. Now see here. Here in this example there is no any f of t or f dash of t, but you should know the function is root t, then its derivative is 1 upon 2 root t. Therefore this is f of t and this is f dash of t. So here we have to apply Laplace transform of derivative result. Okay, we will see the solution. As usual, f of t is the given function 2 into square root of t upon pi. We can write the denominator root pi term with 2. So it becomes 2 upon root pi, which is a constant multiplier to the function root t. Now we will find here first its value at t equal to 0, that is f of 0. Now see here, f of 0 is nothing but f of 0 is equal to 2 upon root pi into square root of 0 is 0. So this term is 0. So 0 into any real number, answer is 0. So here you are having f of 0 equal to 0. Next, now we have to check whether we are getting the same derivative of this function or not. So first, L of 2 upon root pi root t, that is L of f of t equal to Actually here already they have given the Laplace transform result, but still we are checking the result. So it is 2 upon root pi Laplace transform operator, where 2 upon root pi can be taken out of the Laplace operator. So it is 2 upon root pi Laplace of root t, that is t raised to 1 by 2 in index form. Here index of t is not an integer but a fraction. So we have to apply the second formula for the Laplace transform of t raised to n. So this is 2 upon root pi as a multiplier. It is gamma n plus 1 upon s raised to n plus 1. So it is 2 upon root pi multiplier, n is 1 by 2. So it becomes gamma 1 by 2 plus 1, that is 3 by 2, denominator s raised to 3 by 2. Next, gamma 3 by 2 is equal to 1 by 2 gamma 1 by 2. So 2 upon root pi as it is multiplier, this 1 by 2 is from this result, and gamma 1 by 2 value is root pi. So it is root pi upon s raised to 3 by 2. On simplification, 2 get cancelled, root pi get cancelled, and we get 1 upon s raised to 3 by 2. This is just for verification. You may use the given result as it is. Okay, now we will check whether the f dash of t is same as this or not. F of t is this one. So f dash of t, 2 upon root pi as it is multiplier. Derivative of root t is 1 upon 2 root t. So 2 get cancelled, 1 upon square root of pi into square root of t, that is 1 upon square root of pi t. Therefore, we have to use here Laplace transform of derivative result, that is first order derivative result. L of f dash of t equal to minus f of 0 plus s into L of f of t. F of 0 we have find out it is at 0, so this is minus 0 plus s a multiplier into this Laplace transform result which we have obtained, or we may use the given result as it is. Now you have to just simplify using laws of indices for the second term. So it becomes s minus 0, no need to write, s into 1 upon s raised to 3 by 2 means s raised to minus 3 by 2. Now by laws of indices, here s means s raised to 1. So 1 minus 3 by 2, that is minus 1 by 2. So s raised to minus 1 by 2 means 1 upon root s is the answer. And here we are asked to show that whether the Laplace transform of this 1 upon root pi t is 1 upon root s or not. And we have obtained the same results. Hence, we have proved the result. Now using the method of these two examples, solution method of these two examples, and using the results or formulae from the concept of derivative of function, you may solve the examples based on this Laplace transform of derivative result. So for this I have given some examples for practice. Find the Laplace transform of d by dt of t sin 2t. Obviously, first you have to find the Laplace transform of sin 2t, that is from the standard result with a equal to 2. Then multiplication by t property, and then find its value at t equal to 0. Obviously t is multiplier, so when t becomes 0, the function value is 0. So you have to just find minus f of 0 plus s into L of f of t result. Second example, here first obtained the 1 minus cos 2t Laplace transform using the standard result is, then applied division by t property, and then find its value at t equal to 0. Again here for t equal to 0 we get 0 by 0 form. So you have to use the result from the limits and continuity again for this one, and some trigonometric results, and then apply the result of Laplace transform of derivatives. This result is very important, as to solve the ordinary differential equations we need to apply Laplace transform, and hence Laplace transform of derivative is one of the most important concepts from this unit of Laplace transform. Okay, now solve these two examples and try to get the answer correctly. In the next lecture we will try to find the Laplace transform of some higher derivative functions. Okay, thank you.